Hello my dear students, this is Akash HD. Welcome to the AHD physics classes. Hope you all are doing really great. So students, in this video we are going to learn the numericals based upon the torque acting on current carrying coil in a magnetic field. Even we will see energy also, like kinetic energy, potential energy, stable equilibrium, unstable equilibrium, all these things. Okay, so let's start the video. First question is very basic question to understand the concept. A circular coil having n turns and radius r carries a current I. It is held in xz plane in a magnetic field Bi cap. The torque on the loop due to the magnetic field is how much here? Okay. So in this question you can see very well, here I have drawn here one coil is there that is carrying the current. Now torque formula we know very well in a previous video. Torque depends upon the magnetic moment and external magnetic field. So in the question they have given very well the magnetic field in a which direction? Bi cap, that means along the x direction. Okay, so this is the direction of the magnetic field, is it? Now what about the direction of the magnetic moment? So how to get here? Magnetic moment direction depends upon the direction of the current. Okay, so let's take, I'm just considering that the current is flowing like this, na? Like this current is flowing. If we are seeing from upward, anti-clockwise direction. So if I curl my fingers along the current, then thumb is going along the positive y direction, is it? That means this is the direction of the magnetic moment here. Can you see here? This is the direction of the magnetic moment, is it? If in case the current I have made it flow in a reverse direction, then magnetic moment will be in a which direction? Downward direction. Okay. After that, if I write here the magnetic moment direction in a vector form here. So see here please. Magnetic moment formula is M equal to NIA. If I put the vector sign, that means vector M equal to NI vector A. Very, very important basic. That means magnetic moment is always along the direction of the area vector, and area vector is always perpendicular to the plane of the coil. Here you can see when this coil in a which plane? You can see very well xz plane, but the magnetic moment in which direction? Along y direction. That means magnetic moment is always perpendicular to the plane of the coil here. Okay. Now if I just write here the magnetic moment magnitude, so I can write here M equal to Ni and simply A here. Okay, so Ni into area of the coil, how much is there? You can see circular coil is there, and the radius how much here? R, is it? So area of the coil will be how much here? Pi r square here, is it? So this is my magnetic moment. I am just writing here in a which one? Only magnitude I have written here. After that, next one, if I talk about here the magnetic field here. Okay, so magnetic field anyhow in which direction? X direction. Not a problem. You can see here it is given here vector B equal to Bi cap here. Now next one, what is the angle between magnetic field and magnetic moment? So you can see very well magnetic field along x direction, magnetic moment along y direction. That means you can see very well how much angle it is making here? 90 degree. That means angle between magnetic moment and magnetic field how much here? 90 degree. Okay, so here I can solve this question by the two ways. First one, if I just solve with the only the magnitude here. So torque is given by here, torque equal to mb sine theta here. Okay, so what is m? You can see very well here Ni, and you can see pi r square. This is my magnetic moment, magnetic field how much here? B, and how much angle is there? You can see very well 90 degrees. So I can write here, see, sine 90 degrees. So sine 90 degrees is 1. That means what this will come here? You can see here B pi r square in here, is it? So here you are getting only and only magnitude. Even you can see options also. The correct option is here, option B is the answer. But here we are not getting any information about this torque in a which direction. Okay, so for that we can use one more thing is there. You can see very well torque equal to M cross B. What is this? M cross B. So here what will happen that here you will write here M means Ni pi r square. I'm just writing here C M. Okay, and in which direction? J cap, na? Magnitude and direction cross magnetic field means Bi cap. So you can write here C MB. That means anyhow this is the magnitude, and what is the J cap cross I cap? Now see here please. j cap cross I cap. So when you will see here, this will come here, j cap cross I cap means, I'll write here, see, this is the MB, and you know I cap cross j cap means k cap. So j cap cross I cap means minus k cap. So here you can get very well what is the direction of the torque. The direction of the torque is along which direction? Along the negative z direction, because here minus k cap is coming. Even this you can get by the left hand rule also, no? Right hand thumb rule. So you can see very well right hand thumb rule. Okay, so see, we have to curl our finger from first vector to the second vector M to B. So see, M to B, thumb is going inside, that means along a negative z direction. So this is the magnitude and this is the in a vector form. Why we have done this? So that further questions we can understand very well. This is the first one, and you can see very well this is the second one is there, is it? And one thing I would like to tell you again, you can see very well the magnetic field is in the plane of the coil, because coil zx plane and magnetic field along x-axis. So when magnetic field is in the plane of the coil, you can see theta is the 90 degree, is it? Similarly, if I take here the reverse situation, let's take now this is the magnetic field B along x-axis, and now here I have taken just something extra we are discussing here. This coil we have taken in a which plane? YZ plane here. Okay, so in this situation you can see a YZ plane means magnetic field along x-axis, but the coil in a which plane? You can see very well YZ plane here. So here you can see very well the plane of the coil is perpendicular to the magnetic field. The word is coming perpendicular, but what is the angle between a magnetic field and magnetic moment? See, let's take the current is flowing in this direction, no? Like this. So curl the fingers along the current, no? So the magnetic moment will be in this direction instead, you can see here. And here you can see very well the angle how much here? Theta is the 0 degree. Theta is how much here? 0 degree, very, very important. See this one here. So what I would like to tell you, because here area vector is involved, that's why when they are telling the plane of the coil is perpendicular to the magnetic field, that time theta is 0 degree. And when plane of the coil is in the magnetic field, that time theta how much here? 90 degree. Remember that here. Whenever area vector involved, if in the question they are telling perpendicular, that means theta 0 degree. If in case they told parallel, that means theta 90 degree, because here what? Area vector is involved, and area vector means always perpendicular to the plane of the coil. We have taken this much time to understand the basics. Anyhow, see here. Is it? Now we'll go for the next question. The question is here. See here. A closely wound solenoid of 2000 turns and area of cross section, this one, carries a current of 2 ampere. It is suspended through its center and perpendicular. See here the word is telling perpendicular to its length, allowing it to turn in a horizontal plane in a uniform magnetic field, this one Tesla, making an angle of 30 degree with the axis of solenoid. The torque on the solenoid will be how much here? Okay, so you can see very well here. So here I have taken here one solenoid is there, no? Like this current is flowing here, no? Current is flowing like this solenoid, like a coil, helical coil. Okay, so when I will curl my fingers along the current, then thumb will indicate the direction of water. This will indicate the direction of the magnetic moment of the solenoid here, M, along the axis. And magnetic field you can see very well here. This is the magnetic field. And this magnetic field is making how much angle? You can see very well here. Making an angle of 30 degree with the axis of the solenoid. So see, this is the axis of the solenoid. This is the magnetic field, and how much angle is given here? You can see very well. This angle is 30 degree. Angle between magnetic moment and magnetic field, how much here? 30 degree. Okay. So in this situation, which formula I can use here? See, the torque is given by mb sin theta. Always torque is mb sin theta. What is mb? NIA. This is the m into b. M means NIA into b into sin theta. Is it? This is the formula. Okay. After that, let's put the values and all here. Number of turns, how much is given here? See, 2000. That means we can write here, see, 2 into 10 to the power 3. Current, how much? See here. Current is given here, the 2 ampere here. Is it? So see here, current is 2 ampere. Into area, this area of cross section, area of cross section, how much is given here? See, 1.5 into 10 to the power minus 4. This is the area of cross section is there. B, magnetic field, how much is given here? You can see very well, 5 into 10 to the power minus 2 Tesla. Everything in SI unit. And theta, how much here? You can see, theta is the 30 degree, is it? So sin 30 how much here? Sin 30 will come here 1 by 2, is it? Now just cancel the things. What are the things can be cancelled? So this 2 and this 2 is cancelled, and after that you can see 5 into 2 10, and here it will come here, see 1.5, and here you can see here minus 4 minus 2 minus 6 plus 3 minus 6 plus 3 minus 3, and here 5 into 2 one more 0 came. So here you can write here 1.5 into 10 to the power minus 2 Newton meter. Unit of torque will be always Newton meter, never write the joule, is it? So which option is correct here? Very basic, you have to just do the calculation. The correct option is here, option C is the answer, is it? Very well, see, very easy, very easy. Now students, let's move to the next question. The question is here, see, a coil in the shape of an equilateral triangle of side 10 cm lies in a vertical plane between the pole pieces of permanent magnet producing a horizontal magnetic field 20 millitesla. Now, the torque acting on the coil when a current of 0.2 ampere pass through it and its plane becomes parallel to the magnetic field will be this one. The value of x is how much here? See the very well keyword, plane becomes parallel to the magnetic field. So what I told you in the starting, when they are telling parallel word, the plane of the coil is parallel to the magnetic field. So that time theta how much here? The theta will be 90 degree. Remember that here. That is the basic thing, otherwise the complete answer will change. Okay, so theta 90 degrees there. After that, let's see the other data and all. Sides, equilateral triangle of side, how much is given here? The side of the triangle is given here 10 centimeter. That means 10 into 10 to the power minus 2 meter. Okay. After that, what is given here? The magnetic field. The magnetic field is given here, see here, 20 millitesla. That means 20 into 10 to the power minus 3 tesla. Okay. And current how much is flowing here? See here, the current is given here 0.2 ampere. That means 2 into 10 to the power minus 1 ampere. This is the data, is it? Then question is very easy. See here, we know that as torque formula, number of turns is not given. That means only one turn is there. So I can write here torque equal to mb sin theta. Now what is m? M I can write here Ia into b into sin 90 is there, is it? Now current I, number of turns one only. Okay. Area of the equilateral triangle. Remember that the area of the equilateral triangle is always given by root 3 by 4 into side square into b. Sin 90 anyhow one only, is it? Now let's put the value. I how much is given here? See, 2 into 10 to the power minus 1 into root 3 by 4. A square. A how much is there? See, 10 into 10 to the power minus 2. That means we can write here 10 to the power minus 1 meter. Here we have to take the square. That means it will become here 10 to the power minus 2. Is it? Magnetic field how much is given? See, this we can write 2 into 10 to the power minus 2. See here, 2 into 10 to the power minus 2 here, is it? Now let's see what are the things we can cancel. Correct. So you can see here, this 2, 4, and from this 4 this is cancelled. Now what this will become here? Kindly see here, this will become here, see, root 3 into 10 to the power, see here, minus 2, minus 2, minus 4, and here minus 5. 10 to the power minus 5 Newton meter. So root 3 into 10 to the power minus 5 Newton meter, and here you can see very well we have to compare with root x into 10 power minus 5. So what is the value of the x? The value of x is 3. And remember that here the area of the equilateral triangle formula, root 3 by 4 a square. Very basic, you can get in any mathematical book here. Okay, see, great, very easy, is it? Great. Number of turns not given, take 1. Next one, let's see, the question is here, see, a square loop of side 2a and carrying current I is kept in xz plane with its center at origin. A long wire carrying the same current I is placed parallel to the z-axis and passing through the point 0, b, 0 where b is greater than a. Now, the magnitude of the torque on the loop about z-axis is given by how much here? Okay, so let's take here, this is my square loop 1 and this is my wire 2 here. Why I am telling you? Because you can see very well, very basic thing. This is my x-axis, y-axis, z-axis, and here I have taken here 1. square loop. Now this is the side view, that's why it is looking like a parallelogram somewhat. Now what is happening that here in this current is flowing here. Okay, so we will always make sure current is flowing in such a way so that the magnetic moment as much as possible go along the y-axis. Why to make the things complex? So let's take here the current is going I1 how much here? I. Okay, so like this current is flowing here. So curl your fingers along the current, then thumb is indicating the direction of the magnetic moment. Okay, so before also we have seen that now when the coil in a z plane, magnetic moment along y-axis according to right hand thumb rule. Okay, after that what will happen that here magnetic moment we have got it. Now the current here one wire is there now, and this wire is parallel to which axis? Z axis. You can see this is the Z axis and this is the wire. Okay, now what will happen that here in this wire some current is flowing here. Okay, so let's take current is flowing in this direction. You can make reverse also, not a problem. Let's take current is I2 and same current is there, so I2 equal to I. So here you should know the formula of magnetic field of infinite wire. Okay, so Z axis is there like this. So all your fingers along the current, palm towards the observation point O, thumb is going this side, is it? That means what will happen that here the magnetic field of the wire will be along x-axis. This is the magnetic field of the wire, and see here what is the coordinates here? 0, B, 0. That means meaning is what? The distance they are telling. This distance is how much here? B. This distance from here, this perpendicular distance is there, not this distance. This distance is here B. Okay, remember that here. So here you can see very well the angle between magnetic moment and magnetic field, how much here? 90 degree, you can see very well, is it? So from here I can write here the torque formula. Torque is given here again, mb sin theta. This is the basic formula. What is the magnetic moment of this square coil? There you are telling very well. See, the side is two-way. Okay, so m means let's take current how much here? You can see I1, area is A, okay, magnetic field B, and this is sin 90 degree, is it? Now let's take I1. What is the area of the square? If the side is 2A, then area means side square, so you can write here 2A whole square. And B means the magnetic field due to this infinite wire. What is the formula due to the infinite wire? Mu naught current, that means I2 by 2 pi, and this length, how much here? B here. Normally formula used to be mu naught I by 2 pi d or 2 pi r, but here this small r is how much here? B. So mu naught I2 by 2 pi b here, is it? So now we can write here, see, here this will become here, kindly see here, mu naught, what is I1 I, what is I2 I, so I into I, this will become here I square here, is it? Now after that this will become here what? 2A whole square means this will become here the 4A square. Everything we have taken in the numerator, yes, and after that see it is coming here the 2 pi b, is it? Now let's see what other things can be cancelled out here. So you can see very well this 2 is a 4 here. So when you will do here, you can write here, see here, 2 mu naught I square A square by pi b here. Now see again we have used basic formula mb sin theta here, is it? And this is a diagram is there, is it? So which option is correct here? The correct option is here, option C is the answer. Can you see here? Is it? Now students, we'll move to the next one here. Here you can see the next question is C. The question is C. A 250 turn rectangular coil of length 2.1 cm and width 1.25 cm carries a current of 85 microampere and subjected to a magnetic field of strength 0.85 Tesla. Work done for rotating the coil by 180 degree against the torque is how much here? Is it? 180 degree we have to rotate. So first let's note down the data here. How many turns are there? The turns is given here the 250, is it? And length you can see very well. Length is given here 2.1 centimeters, so 10 to the power minus 2 meter. Breadth what is given here? Length, breadth, or we can tell width, anything is okay, not a problem. So what is given here? 1.25 centimeters, so 1.25 into 10 power minus 2 meter. How much current is given here? You can see very well. The current is given here 85 microampere. That means 85 into 10 to the power minus 6 ampere subjected to a magnetic field. Magnetic field how much is given here? See, 0.85 Tesla. Is it? See, 0.85 Tesla. And they are asking work done for rotating the coil by 180 degrees. So initially let's take here angle 0 degree, nothing is given, and how much we are going to rotate? 180 degree, is it? Now students, remember that here, what is the work done formula? Work done by the external force. No, work done by the external force. So this is given by the formula, remember that here, mb cos theta 1. All these things we have covered in a which video? Last video, is it? So mb cos theta 1 minus cos theta 2. What is m? M is given by nia into b, and here we can write here, see, cos 0 minus cos 180, is it? Cos 0 is 1, cos 180 is minus 1. So 1 minus minus 1, that means this will become 2. So here it will become here 2 NIAB. What is coming? 2 NIAB. Now after that here, what we can get here, see, hence work done by the external force, we have to put the data just. So 2, number of turns, what is given here? The 250, number of turns 250, is it? Current, how much is given here? I value 85 microampere, that means 85 into 10 to the power minus 6 into area. Area means length into breadth, that means we can write here, hand writing 2.1 into 1.25 into 10 to the power minus 4, because minus 2 minus 4 here. And what is the value of the B? You can see very well, 0.85 here. Okay, so when you will simplify this, the answer will be 9.4 into 10 to the power minus 6 joule, or we can write here 9.4 microjoule is there. Okay, I have just done the calculation. This one you will get here, 9.4 microjoule. So here you can see there is no other options, 9.4, so we'll choose the nearby option. Option D, 9.1 microjoule is there. Is it? Everything we have put into the SI, so answer will come where? In a SI unit, is it? Great. Now students, let's see, the next question is here, see, a magnetic dipole experiences a torque of 80√3 Newton meter when placed in uniform magnetic field in such a way that dipole moment makes angle 60 degree with the magnetic field. The potential energy of the dipole is how much here? Okay, so here, remember that here in this question, what is given here? The torque is given here 80√3 nanometer. Is it? Nanometer, never joule. After that, what they are telling that here, angle. What angle is given here? You can see very well that theta is given here the 60 degree, is it? And they are asking what? They are asking here the potential energy. Okay, so for that we should know the formula. What is the formula? Remember that here the torque formula is given here, torque equal to mb sin theta, is it? And what is the potential energy formula? U equal to minus mb cos theta. Now, can I divide both this? So if I will divide both of them, let's take here u by tau. Anyhow, mb cancel, and this will become here minus cos theta by sin theta. And what is cos theta by sin theta? Cot theta. So here I can write here minus cot theta. I am making one general formula. So hence we can write here potential energy is given here minus tau into cot theta. This is the general formula, remember that here. Okay, so hence this u will come here minus, what is the value of the tau? 80√3. And theta how much is given? 60 degree. Cot 60 how much here? Tan 60√3. So cot 60 anyhow 1 by √3 here. Is it? So √3 cancel, how much here? Minus 80, answer joule, because U is the energy. So you can see very well minus 80 joule. Which option is correct here? The correct option is here, option B is the answer. Is it? Minus 80 joule. Is it? Great. Now students, let's see, the question is here, see, a magnetic dipole is acted upon by two magnetic fields which are inclined to each other at an angle of 75 degree. One of the fields has a magnitude of 15 millitesla. The dipole attains stable equilibrium at an angle of 30 degree with this field, 15 millitesla. The magnitude of the other field is close to be how much here? Okay, so here the key concept for this question is that stable equilibrium. Stable equilibrium. So stable equilibrium happens when? This happens when theta is 0 degree. Theta is what? Angle between magnetic moment and magnetic field. That means magnetic moment and resultant magnetic field. What I am telling? Magnetic moment and resultant magnetic field should be parallel. Is it? So here what will happen that here? Let's take here. See. So here you can see very well here. Now this I have taken here the magnetic moment. Now magnetic moment M is there, okay, and this magnetic moment is making how much angle from one of the magnetic fields? 30 degrees there. And let's take, this is one of the magnetic field B1, okay, and the magnetic moment is making how much angle from one of the magnetic fields? 30 degree. And in the question they have given the angle between two magnetic fields, how much here? 75 degrees. So let's take here this second magnetic field B2, total how much angle? 75. This is 30. So this is how much here? 45 degree. Is it? So see, magnetic moment is making 30 degree from B1. So B2 will make how much from the M? 45 degree, because total angle 75 degree, 30 plus 45. Now what we want that? We want that the resultant magnetic field should be in which direction? This direction. Resultant magnetic field should be in this direction. B resultant should be in this direction. Is it? So for that, what should happen? That here the horizontal components should cancel out. Is it? That means here if I write here, this side component will be what here? Remember that here? B1, that side cos 30, this side sin 30. So B1 sin 30. Is it? This component will be what here? This side component. This component will be, this is B2 sin 45. A little bit technometry is there here. Okay. So what will happen that here, if we want that resultant magnetic field should be along the magnetic moment direction, then this component and this component should cancel out. Cancel out means they should balance each other here. So what should happen that here? I will write here, see, B2 sin 45 should be equal to B1 sin 30 degrees there. Is it? So I can write here, see, B2 sin 45 value 1 by root 2, and B1 value what is given here? See, the 15 millitesla. I will not change it because options we have to put in a millitesla here. And sin 30 what is given here? 1 by 2. Now after that, when I will simplify this B2, root 2 will go that side, so this will become here 15 into root 2 by 2, that means by root 2, 15 by root 2. And when you will simplify this, approximately this will come here 11 millitesla, because this 15 unit we have not changed, so anyhow answer will come here in a same unit. So correct option is what here? Option B is the answer, 11. And stable equilibrium means you understood very well, theta 0. Unstable means theta 180. We will see in further questions and all. Is it? Now let's see the next question. Very good question. The question is, a circular coil has a moment of inertia 0.8 kilogram meter square around any diameter and is carrying current to produce a magnetic field or magnetic moment of 20 ampere meter square. The coil is kept initially in a vertical position and it can rotate freely around a horizontal diameter. Okay, now let's see. When a uniform magnetic field of 4 Tesla is applied along the vertical, it starts rotating around its horizontal diameter. The angular speed the coil acquires after rotating by 60 degree will be how much here? Is it? So when we'll talk about this question, let's see here please. First we'll note down the data here. So see here. Moment of inertia, what is given here? I is moment of inertia, not a current. So this is given here 0.8 kilogram meter square. Okay. And magnetic moment, what is given here? Let's see here. Magnetic moment means M. Magnetic moment of the coil is given here the 20 ampere meter square here. The coil is kept initially in a vertical position. See, underline the word please. See, vertical position. Coil in a vertical position. And it can rotate in a horizontal diameter. Uniform magnetic field, how much here? 4 Tesla. So B is given here, how much here? 4 Tesla. In which direction? You can see very well. Applied along the vertical. Then they are asking, when the coil is rotated by 60 degree, what is the angular speed? This is the situation. Is it? Can you see very well here? Rotated by 60 degree. Is it? So see, beautifully I have represented here. Here you can see very well. This is the x-axis, this is y-axis, and see, this is the coil. This coil in a which plane? Like this vertical plane is there, is it? Like this vertical plane is there. And you know very well the magnetic field in which direction? This direction is there, no? Vertically upward direction magnetic field is given here. Is it? This is the magnetic field along y-axis. Okay. Now let's take the current is flowing. No? To keep the thing simple, let's take the current is flowing like this here. Is it? So curl your fingers along the current. Thumb is which direction? Inside. That means initially you can see very well the magnetic moment initially is inside here. Now magnetic moment like this here. This is the magnetic field upward. Magnetic moment along the z-axis because cross inside the circle. So initially angle between magnetic moment and the magnetic field, how much here? 90 degrees there. Okay, so see, initial angle is how much here? 90 degree. Initial angle 90 degrees there. Okay, and remember that here initially the coil in a which situation? Rest situation, omega initial how much here? 0. Is it? After that, what will going to happen that here, this coil is going to rotate by how much angle? 60 degrees. So try to understand here. See, this is the magnetic moment inside. This is the magnetic field like this. Going to rotate by how much angle? 60 degree. 60 degree. So when it will rotate 60 degree, how much angle it will make from the magnetic field? 30 degree. Again you see, 90 degree is there. 60 degree rotated. So how much angle it is making now from the magnetic field? 30 degree here. Is it? So remember that here the final angle between magnetic field and magnetic moment will be how much here? 30 degree. In this situation, we have to calculate here the final angular speed. Okay. So now here we are going to use here the conservation of energy. Is it? Conservation of energy always applicable. So remember that here energy at initial position is equal to energy at final position. Initial energy, potential Ui plus Ki is equal to C plus Uf plus how much here? Kf. Okay. Now let's see. Initial potential energy formula MB minus MB cos how much angle is there initially? Here please 90 degrees there, see cos 90. And anyhow magnetic moment M is there, magnetic field B is there, not a problem, no? Because M and B is not gonna change here, no? Because current is fixed anyhow. And plus what is the initial kinetic energy? You can see very well, initially angular speed is 0, so kinetic energy is also 0. Is it? Now what about the final potential energy formula? See, minus MB, and what I have told you very well, when it has rotated by 60 degree, then how much angle it is making? 30 degree. So minus MB cos 30 plus this one will be given here. Now rotation is there, so half I omega square finally. Is it? Now we are just going to simplify this here, very basic. You can see very well, cos 90 means 0, so anyhow minus 0 plus 0. Okay. And here you can see very well what this will come here, see, minus MB cos 30 value, see, root 3 by 2 plus half I omega f square. Anyhow, so left side is not having any meaning, this will come this side, so I can write here, see, half I omega f square is equal to, can you see, MB root 3 by 2. Is it? Now what are the things will cancel out? See, this 2 and this 2 is cancelled out. That means here you can see very well, this omega f is going to come root 3 MB by I. Root 3 MB by I, and again we have to put here one more square root. Is it? Now let's put here the values. So let's take here root 3 into M value. How much is there? M value. Let's see. The M value you can see very well. It has given 20. I value is 0.8. So M value is 20. And I value what is given here? The 0.8. B I think so 4. Is it 4 only? No? Let's see. 4. B value how much is there? See, the B value is 4 only. Okay, 4. So B is 4 is there. Okay. Now after that we'll simplify this. So this will become here, see, 20 into 4, that means 80. 80 by 0.8, that means 100. So this will become here 10 root 3 and one more root 3. Is it? So this will become here 10 into 3 to the power 1 by 4. 10 into 3 to the power 1 by 4. And anyhow, what is the unit of the angular speed? Omega f, that means radian per second. Radian per second. And when you will approximately calculate here, just kindly see very well. Is it? So when you will approximately calculate here, the correct option will come here 13 radian per second, because square root of square root 3 square root of 1.732 approximately you will get here 0.3 into all this. Okay, so I think so 0.13 into 10 will come, or square root of 1.732 no? So it will come some 1.3 then into 10, so 13 will come. Is it? Now let's see here, students. The next question is here. See, the question is, see, a small circular loop of conducting wire has radius A and carries current I. It is placed in a uniform magnetic field B perpendicular to its plane such that when rotated slightly about its diameter and released, it starts performing simple harmonic motion of time period t. If the mass of the loop is small m, then how much here? So here remember that here the keyword is what here? It is placed in a uniform magnetic field perpendicular to its plane. So again I am telling you, see, perpendicular to its plane means theta 0 degree. Theta 0 degree means which equilibrium? Stable equilibrium. Okay. So whenever any object is disturbed from its equilibrium position, it always tries to attain its equilibrium position. So what was there? Remember that here initially I can tell you, see here. So here initially what is happening that here, this, the magnetic moment was in this direction. So when the coil has rotated, the magnetic moment also rotated, is it? So let's take here, when it has rotated by how much angle? Theta angle, let's take, is it? So this is the magnetic moment. Before that, the magnetic moment is like this, but it has rotated by how much angle? Theta. So when it has rotated from its stable equilibrium position, what will happen that here? One restoring torque will develop that will always align the magnetic moment along the direction of the magnetic field, so that theta should be 0 degree, is it? So what I can write here, see here please, the torque formula is given here na, in a opposite direction. So this torque is given by minus mb sine theta. Why minus? Because restoring is there, is it? Now after that here, remember that here the torque is given here, moment of inertia. Moment of inertia, here I am writing here I dash. Why? Because current is given I. Moment of inertia, how much here? I dash. So I can write here I dash alpha is equal to minus mb. Theta is very, very small. So when theta is very, very small, sin theta we can take approximately theta, not a problem. Okay, so see here please. This is the I dash alpha for angular SHM minus omega square theta, and here minus mb theta, is it? Now let's take here what are the things can be cancelled out. See, this theta and this theta is cancelled, anyhow minus minus also cancel. So I can write here omega square means mb by I dash is there, is it? Or we can write here omega means what? 2 pi by capital T, and that side it will become here what? Root mb by I dash. Okay, so from here when I will get here the time period formula, the time period formula is 2 pi root I dash by mb. Okay, remember that here. What is the time period formula? T equal to 2 pi root I dash by mb. Kindly see here very well. After that we have to just put here the somewhat values and all answer will come, is it? So see, now we can write here this time period is given here. Okay, 2 pi I have sent inside because question requirement is there. 4 pi square, 2 pi went inside. What is I dash? Moment of inertia, is it? So moment of inertia is given here, kindly see here, m into I dash, m into circular loop is there, na, a small circular loop of radius around the diameter, see, around the diameter for the circular loop, moment of inertia is how much here? Mr square by 2, but here what will become here? Ma square by 2 here, okay? Ma square by 2 I have taken this side. Yeah, this is the moment of inertia about the diameter, okay? After that we have put the value of I dash, and what is the magnetic moment? Magnetic moment is given by I into area. What is the area? Area is given here pi a square, correct na? Area because radius is a pi a square, and what is given here? Into b. Okay, now students, let's cancel out the things here. So here you can see very well, from this pi, 1 pi cancel, from this a square is cancelled. So what this will become here? Kindly let's see. And this here, see, this 2 2 is 4 is there. So here it will become here, see, 2 pi m by I into b. 2 pi m by IB. See, anyhow the formula is this one, but when you will put the values and all, it will come here. Which option? Correct option C is there. Kindly see here, is it? So students, I hope so. This video based upon the questions of the torque, energy, stable equilibrium, unstable equilibrium is very, very clear to you. Keep studying, keep growing.